critiquing and admiring the other's artwork.
I feel bad.
There she is.
It looks very bright.
Yeah, the sun's decided to appear for a while.
I was like, I think I was just out. I had so much to do, and then I just was like, so hectic.
Okay. All right, we'll get started here. We're talking about polar coordinates. So that's that other system of plotting a point on the plane. And we have this relationship between the polar coordinates and what are called the Cartesian x and y coordinates. So the cosine of the angle theta is equal to x over r. The sine of theta is y over r. R is that we have a point here. R is that distance from the point to the what's called the pole. This is our angle theta that's made with the polar axis. Another thing, and so this is our point r comma theta, and previously with Cartesian coordinates we called it, of course, x comma y. So another thing we have here is with the Pythagorean theorem that r squared is equal to x squared plus y squared, or when you take the square root of both sides, r is equal to the square root of x squared plus y squared, and also that the tangent of the angle theta is equal to y over x, the opposite over the adjacent. So these are all equations or identities that you need to have at your fingertips. So what we're going to do next here is we're going to do a couple of sketchings of curves here. Now, this one, r equals 2 cosine of theta, we actually were looking at that at the end of class the last time, and we converted it into the Cartesian coordinates. And if you look at your notes, what we got here was a circle, x minus 1 quantity squared plus y squared equals to 1. This is the Cartesian equation. And of course, this is a circle with a center of 1 comma 0. So it's a circle like this with a center equal to 1 comma 0. All right. Okay, so this time though, we're going to sketch this thing, not converting it to the Cartesian, but just working with the polar equation. All right. So let's just start a table here. We'll put our theta here, and we'll put our r here. R is equal to 2 times cosine of theta. And we'll, just like we do with other graphs, we'll get a table. So when theta is equal to 0, then r is equal to 2. When theta is equal to pi over 6, this is going to be 2 times the cosine of 30 degrees, so that's going to be 2 times the square root of 3 over 2, which simplifies to the square root of 3. And when it's pi over 4, we're going to have 2 times the cosine of pi over 4, which is the square root of 2 over 2. Let's see, square root of 2 over 2, right, all right. Okay, and the 2's cancel out, and we end up with the square root of 2 for our R value. And let's go up to 60 degrees then, pi over 3, see what we get there. 2 times the cosine of pi over 3 is 2 times 1/2. So that simplifies to 1. And then when we go to 90 degrees, the cosine of 90 degrees is 0, so we have a 0 there. And let's do a few more all the way to pi here. Let's go over here. 2 times the cosine of theta. Okay, let's look at 2/3 pi, which is 120 degrees. So we remember here, let me draw a quick ASTC. All students take calculus. So we know that the cosine is going to be negative in that area, and our reference angle is going to be pi over 3, 60 degrees. So we end up with then 2 times a negative 1/2, which gives us a negative 1 then for that answer. And let's go to 3 pi over 4, which is 135 degrees. Okay, so again, we're going to have a negative cosine, and that's going to be 2 times negative square root of 2 over 2, which is the negative square root of 2. And then let's 5 pi over 6, which is 150 degrees. That's going to be 2 times, let's see, the reference angle is going to be pi over 6, so that's 30 degrees. So the cosine of 30 degrees is square root of 3 over 2, but we have to have a minus there because it's in the second quadrant. So we get a negative square root of 3. And then finally, let's just look at pi. And the cosine of pi is a negative 1, so it's 2 times negative 1, which is negative 2. All right, so we have a whole bunch of points here, and so probably an overabundance of points, we should be able to graph this thing. So let's take our polar sheet here. Let's see if I can, let's start with the first few there. All right, and so, okay, let's mark out, let's see, 0.5, 1, 1.5. This is 2. That's 2 over there also, just so I can keep track of it. So when theta is 0, r is equal to 2. So that's the point right there. So let me mark that down. And then when we are at pi over 6, which is this ray or line right here, we're at the square root of 3. Now the square root of 3 is roughly 1.7, all right? So that's going to be somewhere like here. Are we okay so far with graphing this? Then let's go to pi over 4, and this now is the square root of 2. Well, square root of 2 is what, roughly 1.4. So this line down here is 1.5. So we're going to go just a little bit inside of that to get 1.4. And then pi over 3 is equal to 1. So that is, here's pi over 3, and here is, wait a minute, where's 1 at? I think I've already messed up here on my graph. So why don't I start some points over again? All right. Okay. This is 2 right here. Okay, then pi over 6, square root 1.7. So this is 1.5. So 1.7 would be a little bit out from that. Pi over 4 is going to be a little bit in 1.5, so it's going to be like that. All right. Okay, sorry about that. And then for, what's the next one then? Pi over 3, we're going to be at 1, so let's go out 1, and that'll be right there for pi over 3. Okay, then at pi over 2, we're down to 0. So here's our pi over 2, and we're down at 0 right there. Okay, and basically what this is the top half of our circle. all right? Now, let's look at the other points we have here then. When theta is equal to 2/3 pi, so here is 2/3 pi over here. Notice that our r is now -1. So I go along the line for 2/3 pi, but I now go in the negative direction, the other direction, and I go to, careful with this, I go to where I have the 1. So it's going to be the -1 there. Okay, 2/3 pi, -1. So I want to make sure we're all clear on that. When that r is negative, we go to the opposite side to graph it. Jenna, you all right with that? Okay. And then when we're at 3/4 pi, we're at -√2. So here's 3/4 pi, go down, and this is 1. 1.5 is there, so it'll be roughly on the inside there of that 1.5. Is that right? Okay. And then when we're at 5 pi over 6, which is this ray right here, we're going to have a -√3. So 5 pi over 6, we trace that, and we're going to be a little bit on the outside of 1.5, like that. Okay. And then finally, when we're at pi, which is this line right here, we're at -2, so we're going to go back in the other direction, and we had already plotted that point. Okay. And then we attempt to connect these with a smooth curve. And that's as good as I can get. I definitely need the drawing class next door. So that's what we have, and this is then the same thing that we came up with before, except we plotted it using the polar coordinates. Again, this is a circle with in the same area of the plane. Does anybody have any questions just on this plotting? The big thing is just like the mistake I had made. You got to be careful that you're on the correct circle going out, which I was not very careful of. All right, I want to do another one then to plot, and this one is r equals cosine of 2 theta as theta goes from 0 to 2 pi, right? And let me put my little ASTC business here to remind me of how things are positive and negative. And I'm not going to do a careful table with this. We're just going to kind of see roughly what this thing would look like. All right. So what we're going to start with is at theta equals 0. So when theta is equal to 0, r is equal to the cosine of 2 times 0, which is the cosine of 0. So therefore, r is equal to 1. So let's just plot a 1 there, and that would be our r right there. Okay. Now, as we go, let's just look at the next point here of, let's look at pi over 4. Okay, so that's the theta I want to look at next. So when theta is pi over 4, r is equal to the cosine of 2 times pi over 4, which is the cosine of pi over 2. The 2's cancel out there, and we know that the cosine of pi over 2 is 0. So therefore, what this is going to do here in this direction, like this, it's going to go to 0 as we go from theta equaling 0 to theta equaling pi over 4. It's going to go in this direction like this. So let me just label this 0 to pi over 4. It's going to travel like that. Any question on that? I didn't do the details of the other points in between. We know that it's going to be positive values because cosine is positive in the first quadrant. Okay, we all right with that? Okay, let's then go from pi over 4 to pi over 2. Now, when this happens, our cosine now ends up in the second quadrant. So from pi over 4 to pi over 2, when we have to multiply it by 2, so we have pi, so times 2, we're going to be going from pi over 2 to pi. And we know there, that's in our second quadrant, the cosine is negative. All right? So we're now going to be heading, basically, in this direction right here. We're going to suddenly just drop down. Oh, no, I'm sorry. We're not pi over 4 to pi over 2. We're going to be here. We're going to go down here then, because our angle is going to be right here for theta, pi over 4 to, it's going to be pi over 4 to pi over 2, but our values are going to be negative, so it's going to be on the other side here, and now we're going to go this way, like this. Okay, and my drawing looks off already, but this is from pi over 4 to pi over 2, like that. Okay, so we're going to be in that opposite quadrant because we have negative values. And then we want to go then from, let's continue going from now from pi over 2 to, say, 3/4 pi. So when we do that, let's multiply our angle by 2. We're going from pi to, let's see, 2 times 3/4 is 3/2. We're going from pi to 3/2 pi. And again, our cosine is negative in that's the third quadrant. They're negative values. Okay? ASTC. So we're now taking values of theta up here from pi over 2 to from pi over 2 to 3/4 pi, but our values are going to be negative, so we're going to be dropping to the opposite quadrant. So now we're going to be going like this. Another loop like that. Okay. And we continue this process actually then. So this, let me mark this. This would be pi over 2 to 3/4 pi. And we just continue. It's going to give us a clover leaf type thing. So we're now going to be going like this in this direction, and that's going to be for theta values from 3/4 pi to pi. Okay. And then we're going to just continue along. Then we're going to go like this in this direction, and that'll give us theta values from pi to, let's see, it'd be 1 1/4 pi. That'll be 5/4 pi. And then we loop around again like this, and that'll be values of theta from 5 pi over 4 to, let's see, that's 1 1/4. So that'll be, what is it? We want to go to 1 1/2, 3 pi over 2. And then we're almost done here. Then we go, and then we'll loop around like this. And that's for values of theta from 3 pi over 2 to 7/4 pi. And then finally, we make our final loop here. And that's for values of theta from 7 pi over 4 to 2 pi. Okay. So ignore the lopsided leaves here. What we end up getting with this is looks like a 4-leaf clover. It's in the literature. It's called a 4-leaved rose. All right. Okay. All right. Now, so that's what we get just by using the polar coordinates. Now let's let's also find the corresponding Cartesian equation. Find the corresponding Cartesian equation or function. And so let's see here. What do we have? We're starting with r equals cosine of 2 theta. So remember, there were some formulas here that I said you guys need to make sure you remember for this section, and we had given those the last time. One of them being this, that the cosine of 2 alpha is cosine squared minus sine squared. The sine of 2 alpha is 2 times the sine of cosine. So we're going to use this second one here, cosine of 2 alpha, and we're going to change this then to the cosine squared of theta minus the sine squared of theta. Right? Now, so this is equal to r. Now, the cosine of theta and the sine of theta we can represent in terms of x. We have this formula back here that the cosine of theta is x divided by r. The sine of theta is y divided by r. So the reason I wanted to get things here, I wanted to go from 2 theta to a single theta so that I could then replace the cosine with x over r and the sine with x over r. So now we get, so therefore I'm using cosine of theta equals x over r, and I'm using sine of theta is equal to y over r. Okay, so what I get here is I get r is equal to, okay, the cosine squared is going to be x squared over r squared, minus the sine squared is going to be y squared over r squared, like that. Okay. All right. What might we want to do then to both sides of this? Yeah, let's just go on let's get rid of the denominator. Let's get all the r's together. We multiply by r squared. All the r's are going to be on the left side. So I get r to the 3rd power now on the left, and then I get that equals x squared minus y squared. Okay. And then finally, the last thing I want to use here is the fact that r is equal to the square root of x squared plus y squared. All right, that's identity. But however, this time I have r to the 3rd power. So this is really, I can do this in a couple steps if I like. R, of course, is square root of x squared plus y squared. But I'm raising it to the 3rd power, and that equals x squared minus y squared. And then and so this is fine, but another way that I can represent the left-hand side, as I can represent it as x squared plus y squared, and what exponent would it be raised to? 3 halves, right. The 2 on the bottom is because we have a square root, and the 3 on top is because we're raising it to the 3rd power. So this is x squared plus y squared in parentheses to the 3 halves power is equal to x squared minus y squared. And that's a Cartesian representation of that 4-petaled rose that we graphed. Question on the conversion. Sometimes you have to have a little bit of cleverness with the conversion here from the polar to the Cartesian. But in essence, what you're going to use, you're not going to use anything more than what we have up here. Yes, Jenna?
What would you use in the equation part? Because we can't, like, graph it.
Right. Well, the thing with the Cartesian equation is that it represents things in terms of x and y. And so x is horizontal, y is vertical, all right? And so a lot of times that's how we want to see things. because say we want to do a derivative of this or something like that, we live in an up horizontal world. We don't live in a polar world where everything is concentric and going out. So I can just say that there are times we want to see it and in this grid-like way of the Cartesian way. Okay. Let's see. I think I have another. Yeah, we have one more here. And before we get into some, because so far we haven't been talking about any calculus stuff with this. We've just been graphing stuff and showing the relationship between the polar coordinates and the Cartesian. Let's just do one more here. And this one also has a name to it. And so it's r equals 1 plus the sine of theta. All right. And let's just do, again, a very rough graph of this to see what it might look like. Okay. So when theta is equal to 0, r is equal to 1 plus the sine of theta. So the sine of 0 is 0, so r is going to be equal to 1. So right here at angle 0, we're going to go out 1, and that'll be a point there on our graph. Okay, let's just jump to pi over 2. When theta is pi over 2, r is equal to 1 plus sine of pi over 2, and that's a 1, so it's 1 plus 1, so r is equal to 2. So let me jump up 1, 2 here, and we'd have a point up there. All right, let's then look at pi. Let's jump to the next quadrant, pi, and we have r is equal to 1 plus the sine of pi, and that's going to give us back to a 1 again, right? So here is our angle pi when in the polar coordinates, and we're going to go out 1. So that's that point right there. And then finally, let's look at 3 pi over 2, 270 degrees. And r then is 1 plus sine of 3 pi over 2. But what's the sine of 270 degrees? Negative 1. Remember our little unit circle thing right here. The 270 degrees, x is 0, y, which is the sine, is negative 1. So this is 1 minus 1. So at that angle, our r is equal to 0. So we're going to go back up into here. And then finally, going to 2 pi, we end up getting the same thing that we started out with. We get a 1. So if I try then to, let's go in this, so we went like this, we went like this, we go like this, we go like this, and this is the direction that we went through. Now this particular thing kind of looks like an upside down heart, so it's got a name. It's called a cardioid. From cardiovascular heart, okay? That's what it's called, because it looks like a heart. Let's get the corresponding Cartesian equation. Cartesian equation. So it's r is equal to 1 plus sine of theta. What might be the first thing you want to replace with, and what would you replace it with? What's the sine of theta equal? Y over r. Right, so let's do that. So we have r is equal to 1 plus y over r, all right? And then like we did before, let's multiply everything by the denominator r. So we get r squared is equal to r plus y, all right? And so, finally, we can use what r is equal to. Now, r squared is equal to x squared plus y squared. equals plane R is equal to the square root of x squared plus y squared, and then plus y on the outside. So that's the kind of Cartesian equation that we would get from this. Question on that and how we derive this, just using those few of those basic identities. Okay. Because I know that you will be responsible for some kind of simple graphing on the next test. Something not terribly complicated, but being able to put it together from a table, all right? Okay, just a couple other things here before we get into the calculus of it. If we R equals sine of theta, I'll just tell you, if we do it, it's going to graph like this. It's going to be a circle at 0, 1 if we look at it in terms of Cartesian coordinates. R equals cosine of theta, it's going to be here, like this, off to the side when we graph it. R equals cosine of n times theta, and R equals sine of n times theta, where n is a whole number. Okay. A whole number. Okay, basically what they're going to look like is this. If n is even, these are going to have 2 times n leaves or loops. If n is odd, it's going to have n leaves or n loops, like that. Okay. And we saw that previously here with the cosine of 2 theta. This is an even number, that's our n, and notice we had 4 loops with that one, okay? So let's say that r is equal to the cosine of, say, 3 theta. Now that's an odd number. So we're going to have 3 loops, all right? And it's going to look something like this. We're going to have a loop here. Oh boy, here we go with drawing. And we're going, let's see, we're not going to, we're going to be 0 there. We're going to have a loop, I think that's going to be there. Ooh. How is that going to look? Should have drawn this out. This is going to all be from 0 to pi over 2. And from pi over 2 to pi, it's just going to be this loop again. From pi to 3/2 pi, it's going to be negative. So we're going to have something that doesn't seem, we're going to have something like this. I don't know if it's going to look like this or not. I'm sorry. I wonder if that doesn't seem right. Let me look, see if the book has a nice handy thing. I wasn't planning on drawing it. I thought I would just draw it without preference. So let's see. Let's the sine. Mm-hmm. Mm-hmm. Okay, they don't give it. It's going to have 3 of them. You got it? Ah, Nelson saves the day with Wolfram. No, don't take it away yet. Thanks, Nelson. I'll remember you on the next test. The first loop does look like this, but then the second loop goes this way, and the third loop goes this way. All right. Thank you, sir. Okay. All right. Let's see. Let's then go to looking at tangents of these. So let's finally get to some calculus stuff. So let's look at the tangents to these polar curves. All right. Now, a polar curve is something like r equals a function of theta. This is a polar curve. All right. Now, what we're wanting to figure out is we're going to now want to see what these derivatives are like in the Cartesian system, because that's the up and sideways system. That's how we're used to looking at things. So we want to calculate dy dx. And it's going to turn out it's going to be the same way as it was with the Cartesian system. Oh my God. These people don't have any sound, isn't that? What happened?
Oh, the tech guy down, so the next mic show up and down.
You haven't heard a word I've said, is that right? How long have you been all right? Because that was at 10:17 you typed that. Oh, that's good. So it's all right. And I have no idea what happened, so I'm sorry about that. But I'm all right. Okay. They're fine now. They've been fine for 20 minutes, but they've had like 20 minutes where they didn't hear a word I said. Okay.
On YouTube.
Huh? Yeah, well, we'll see what happens with that, too. All right. So we want to calculate dy dx. We want to look at the Cartesian system here. So it's going to be dy d theta over dx d theta, just like we did with the parametric equation. So it's just like we're dividing each numerator and denominator by d theta, all right? So we've got to figure out what dy d theta is and what dx d theta is. So for that, we're going to go back to our formulas that x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. All right. Now, r here is a function of theta. R is equal to f of theta. So x is equal to some function of theta times the cosine of theta. I'm just putting f of theta in place of r. Similarly, y is equal to f of theta times sine of theta. All right. Okay. So let's do, first of all, at the top here, we need to do dy d theta. So what we're going to have to use here is we're going to have to use the product rule. In fact, let's do it right down here. Dy d theta, got to use the product rule. It's going to equal, let's say it's going to equal df d theta times the sine of theta plus f of theta times the derivative of the sine, which is the cosine of theta. All right. We okay with that product rule? So up above here in my formula, I'm going to go along with how the book has it. Instead of writing df d theta, I'm just going to write dr d theta here. So dr d theta times the sine of theta plus, and now instead of writing f of theta, I'm just going to write r plus r times the cosine of theta. So that's our numerator. In our denominator, we have to get dx d theta, and again, we have to use the product rule. So dx d theta, okay, again, I do the derivative of f with respect to theta times cosine of theta, and then I do the f of theta times the derivative of the cosine, which is negative sine of theta. And so I'm going to then write that up here in my denominator. I'm going to write df d theta. I'm going to use r in place of f. That's dr d theta times the cosine of theta. And now I'm just going to put here my minus sign to the front, minus, and I'm going to replace the f with the r, minus r times the sine of theta. That's our formula that we need to remember for the derivative. This is for the derivative of a polar curve in terms of theta and r, in terms of theta, actually. All right. So, and actually, let me just point this out. You don't have to do a whole lot of memorizing with this. You understand that it's going to be dy d theta over dx d theta, just by dividing by the theta, d theta. You can actually, if you blank out on this, you can just recreate this the way I did here. X is r cosine theta, y is r sine of theta. When you do the derivative, you have to use the product rule, and you will get the numerator and denominator if you fail to remember it. Okay. I want to do an example here where we have r is equal to the sine of theta, and we want to find dy dx in terms of theta. Okay, that's our problem. All right, so let's just start by this. Y is equal to r times the sine of theta. That's the by definition of. And r that we are given, the r that we are given, r equals the sine of theta. So I'm going to replace the r here by what it is equal to in our polar equation, and this is going to be sine of theta times sine of theta, so that's sine squared of theta. So y is equal to sine squared of theta. X is equal to r times the cosine of theta. That's our identity. Now I'm going to replace the r by what our curve is. So x is equal to sine of theta times the cosine of theta. All right? So let me put boxes around these two for y and for x. And so you see here, actually, you don't really have to worry about memorizing this, the formula that I just gave you. Okay, we want to get dy dx. So dy dx is dy d theta over dx d theta. Okay? All right. So now I need to find, I have my y is equal to sine squared of theta. I need to find its derivative with respect to theta. My x is equal to sine cosine. I need to get my derivative down below with respect to theta. So, for the top one, y is equal to sine squared of theta. I need to use the chain rule. I bring my exponent down, 2 times the sine of theta, and then I have to multiply it by the derivative of the sine. So that's the cosine times the cosine of theta. Chain rule. All right. dx d theta, I need to use the product rule. Okay, so we have derivative of the sine is the cosine times the other function plus sine of theta times the derivative of the cosine, which is negative sine of theta. All right. So let's see what we have here. We have 2 sine theta cosine theta on top. Down below, I can write this a little bit nicer. Cosine times cosine, cosine squared theta minus sine times sine, sine squared theta. Okay. Okay, this is fine. But can I just simplify that, make it look even nicer for the top and the bottom? And Nikisha, what can I do with it? Right, that's exactly it. The top, 2 times sine theta cosine theta is the sine of 2 theta. Okay? That's one of those formulas that yesterday when we had our 5-minute trig class, one of those formulas. Cosine squared minus sine squared, that's the cosine of 2 theta. All right. And then we have sine over cosine of the same angle. Sine over cosine is the tangent and the angle of 2 theta. So that can be simplified, in this case, very nicely. All right. Okay, so we end up at dy dx equals the tangent of 2 theta. All right, so let's say you were then, in addition, you were asked, find the slope of the tangent line at theta equal to pi over 6. Right? Well, we know that the derivative value gives us the slope of the tangent line, so we just evaluate dy dx at theta equals pi over 6. So what does that give us? dy dx is the tangent of 2 theta, so that's going to be the tangent of 2 times pi over 6, which is the tangent of pi over 3, 60 degrees, and that's what? Square root of 3, right. From your special triangle. So that would be so m, if you want to call m the slope, m is equal to the square root of 3. Okay. All right. If I guess we'll do this. If we wanted to know the equation of the tangent line, I've already got the slope, but what I need to find is the x point and the y point, all right? So what do we have here? We have x is equal to, we found it up here. Oops, where is it? Oh yeah, here it is. X is equal to sine theta cosine theta. Y is equal to sine squared of theta. So we can use those. We plug in a pi over 6. So x is equal to the sine of pi over 6 times the cosine of pi over 6. And so what's that going to give us there? X is equal to x. Sine of pi over 6 is what? 1/2. Cosine of pi over 6? Square root of 3 over 2, right? So our x value, when we multiply together, is the square root of 3 over 4. And therefore, and let's get the y value. Y is equal to sine squared of pi over 6. Okay? So the sine of 30 degrees is 1/2. So that's 1/2 squared. So our y value then is 1/4. So therefore our equation would be, we just use the point slope formula, y minus y naught equals m times x minus x naught. And we would get y minus, what, 1/4 is equal to the square root of 3 times x minus the square root of 3 over 4. All right? Okay. All right. I want to look at one more here. Why don't we take a 5-minute break, and we'll do another dy dx then. Or what's that? Are you
excited for this weekend?
Why? What's going on?
School.
Just no school?
Yeah.
Just being out of school? All right. Well,
I
that's
already did the homework for
I'm-
2 Mondays.
good. That's good. You can start on the one for the following Monday. But not this weekend.
This week.
All right. I'm always excited about the weekend myself. I can sleep a little bit later in the morning.
Also, it's my birthday next week on Wednesday.
On Wednesday.
Yeah, Wednesday next week.
Oh, okay.
She's going to the week usually. She's the third.
There we go.
My cousin's birthday was on the 11th.
Oh, so you
He's dragging out on 20 or whatever.
Oh. So she's older than you.
By 9 days.
Right, 9 days, right. So she'll always be older than you.
It bugs me because I'm pretty sure on her
She'll
20th.
always be older than you.
On
And that's a good
21st birthday, I'm sure I'm going to get a lot of crap.
Oh, that'll be the big thing, the 21st, yeah.
But once you hit 30, you can really think you're old.
You're old, because you've got 9 more days before you hit 30. That's right. You'll start to be thankful you're younger. That's right.
You know, yeah, right.
But until then, especially on the 21st birthday, she's like, ha, I'm having more fun.
That's right. Well, that's, yeah.
Even if it's 9 days, still can't.
That's true. That's true. Well, yeah, that's right. That's a big one.
Yeah, when you're 20, you're no longer a teenager, but you're also not old enough to.
Right, right. That's okay. You'll have plenty of time to drink once you're 21.
Mm-hmm. I don't plan to
If that's, so be careful with that.
I don't plan to get hurt. Although I'm pretty sure that's why 21-year-olds then drink a lot.
When I was 8, when I was 21, I was living away with him, but his age was 18.
Oh, yeah.
So we think after I moved there.
Mm-hmm. That's a little bit, that's too young, I think.
I think they didn't make it a big deal that when you turn 21 spring, you want to get pushed down, bro.
Well, I don't know how many young people wait until they're 21.
Well, I can do it in public. That's
Right. Mm-hmm. Right. You can't go to a cocktail lounge or a bar and order.
If you're legal and drink, you can look at you're taller than the bar. That's the rule I grew up with.
Yeah.
I grew up with a bunch of Irish.
Oh. Then watch that drinking, Kyle. You got some genetic factors there working for some big time drinking. I'm Scotch-Irish, so I know that.
I just thought that's the funniest tool. If you can look over the bar, you can get something to drink.
Yeah.
Except for water. You can drink that water.
Well, I hope someday you can go to Ireland. It's a really, really wonderful place to visit.
Where I plan to go at least once.
It's really, yeah, I've been to Edinburgh, and that was really nice. I'd like to see more. My grandmother and grandfather are from Glasgow, but I haven't made it there yet.
I sort of want to do a tour through Europe during my honeymoon.
Okay.
I was going to say that now.
Did you say?
Too many people read there.
What did you say? During your first honeymoon?
Yeah. I got married.
It's not an anniversary.
Already planning the
Not
second
an
one.
anniversary, my bad.
Okay. All right. I think we'll get started here with this. I just want to do another example here of finding this. Oh, Jenna isn't here yet. Oh, well, she'll be here soon.
Oh, well, forget it.
She will be here soon. Okay, here's another one. Again, we're getting this dy dx, find dy dx in terms of theta. And the polar curve we're given is r is equal to cosine of 2 theta, all right? So just for grins, we know that roughly this curve is actually going to look like something like that, all right? No, I'm sorry. It looks like this. It's the 4-leaf deal. Okay. All right, so we want to get, first of all, we have to get dy d theta and dx d theta. So first of all, we have y is equal to r sine of theta. And I'm going to replace the r with our curve of cosine of 2 theta. So y is equal to cosine of 2 theta times the sine of theta. And so let's go on and get dy d theta here from this. All right, so we're going to have to use the product rule. let's take the derivative of the cosine. That's going to be the negative sine, but it's going to be negative 2 times the sine of 2 theta. And then we multiply that by derivative of that times this times the sine of theta. And then we take plus, and then we take our first function, cosine of 2 theta, and multiply it by the derivative of the sine, which is the cosine of theta. So that's our dy d theta. Let's get x. X is, of course, r times the cosine of theta. So our r is the cosine of 2 theta times the cosine of theta. And again, we're going to have to use the product rule for dx d theta. All right, so let's start with the derivative again of the cosine of 2 theta is the minus 2 times the sine of 2 theta. And then that's going to be multiplied by the cosine. And then plus just the cosine of 2 theta. Derivative of the cosine is the minus sine of theta. All right. So that's, let's just rewrite that. That's minus 2 sine of 2 theta, cosine theta. Let me put the minus out front here. Minus cosine of 2 theta times the sine of theta. All right. Okay, so have to do a little work there to get those. So therefore, dy dx is going to be equal to dy d theta on top over dx d theta on the bottom. All right? So we're going to get quite a little formula here for this. Let's just copy down what we got. Dx dy d theta comes first, so that let's copy down that. Minus 2 sine of 2 theta times the sine of theta plus cosine of 2 theta times the cosine of theta all over the dx d theta. Minus 2 sine of 2 theta cosine of theta minus cosine of 2 theta times the sine of theta. All right. All right, so no simple formulas here. I want to emphasize the fact that you don't have to memorize anything for these formulas. You just need to know that dy dx is going to be dy d theta over dx d theta. You're going to remember that y is r times the sine, that x is r times the cosine. And all you do for replacing the r, you replace the r with the polar curve that you are given. In this case, we were given cosine of 2 theta. And then you use your chain rule and your product rule to get those two respective derivatives. All right, so we have this. And let's suppose that we're asked to find the slope of the tangent line, again at pi over 6. Find the slope of the tangent line at pi over 6. All right. So let's see here. That's going to give us, let me say m is equal to, now I just plug in pi over 6 here. Minus 2 sine, now that's 2 times theta, so that's 2 times pi over 6. So let me just right now put pi over 3 times the sine of theta, sine of pi over 6, plus cosine of 2 theta, so that's going to be pi over 3. Cosine of theta is cosine of pi over 6, all over minus 2. Sine of 2 theta again, so that's going to be pi over 3. Cosine of theta, so that's going to be cosine of pi over 6. Oops, that's a minus. Cosine of 2 theta, again, that's pi over 3, times the sine of theta, sine of pi over 6. All right, let's see what we get here with this. Minus 2. What's the sine of pi over 3? Square root of 3 over 2. If necessary, just draw your special triangle out on your paper. pi over 3, pi over 6, 1, square root of 3, 2, and go from there. All right, and then the sine of pi over 6 is going to be 1/2 plus cosine of pi over 3, that's going to be 1/2, 1 over 2. Cosine of pi over 6, so we're back up to this angle, is going to be the square root of 3 over 2. So we've got kind of a mess up there, and we're going to have kind of a mess down below also. Minus 2 sine of pi over 3 is now going to be square root of 3 over 2. Cosine of pi over 6 is square root of 3 over 2. Minus cosine of pi over 3, 1/2. Sine of pi over 6 is also 1/2. All right. Okay, so let's take this mess and try to simplify it as much as we can here. Okay. Let's see. We've got basically here, we have a minus 2, and it's on top here, we got a 2 times 2 on the bottom. So that can simplify as, let me just do it this way. And that, we can take our minus 2 and then multiply these two together, square root of 3 over 4. And then we can multiply these two together and we get a square root of 3 over 4. And then let's go to the bottom. A minus 2, again we're going to multiply these two together here. Now this time when we multiply them together, we get what? 3 over 4, right? Square root of 3 times square root of 3. Then we have a minus here. 1/2 times 1/2 is 1/4. Okay. All right. Let's see. What's the top part right now? What can I do with that top part? Cross out the 2's. Yeah, just add them together. If you notice here, Jenna, we've got a minus 2 times the square root of 3 over 4, and then we're adding 1 times square root of 3 over 4. So basically, we can, when we combine them together, we have a negative square root of 3 over 4 on the top. Okay. The bottom, let's see, what do we have? This is what? Minus 6/4, that's minus 3/2, minus 1/4. Okay. All right. What do we want to do from here? There's a couple different things we can do, but I'll take any suggestion. Okay, that's fine. What would be a common denominator on the bottom? 4. Okay, we could do that. So we have minus square root of 3 over 4 over, and what will we end up with there? Negative 7 over 4, right? Because we're going to have negative 6 over 4 minus 1 over 4, so we're going to have minus 7 over 4 in the denominator there. Okay. Now what will I have then? Square root of 3 over 7. We got the same denominator, multiply by 4. You get rid of the 4 in the denominator. We've got a double negative. So this thing finally simplifies to the square root of 3 over 7. Okay. So you had to do a little bit of work with that one to do that. All right. So that, as far as the calculus thing, that in this section, that's the only calculus thing in this section, is given a polar curve, compute the dy dx, and then maybe be asked to get the slope of the tangent line. All right? So that's the kind of thing we have in this section. let's go on then to the next section, 10.4, and we'll be able to get some headway through this. Because we have three more sections, 10.4, 10.5, and 10.6, all right? And then that's the end of Calculus 2. So let's get started here on these last three then, 10.4. And 10.4 has to do with computing areas and arc lengths with the polar coordinates. Computing areas and arc lengths in polar coordinates. Okay. So what I want to start out with here is just looking at a plain old circle. We're going to look at this thing first, areas. And let's just look at a circle. And what's the area of a circle with radius r? Pi r squared. So it's pi r squared. Oops, pi r squared. Okay. Now, what if we just want to take a piece of this circle and get the area? Let's say a piece that has an angle, that's called the central angle of theta, for instance. Now, what's the angle that we have if we go all the way around the circle? What's that whole angle going to be? Well, what's another way with radians of saying 360 degrees? 2 pi. So the whole thing is 2 pi. So if we're just looking at a piece of this, we're, say, of angle theta, the area there is going to be that angle theta divided by my entire angle of 2 pi times pi r squared. All right? So this is equal to the area of that pi-shaped piece. And let's simplify this a little bit, and what we get, let's see, the pi's cancel out, so we have 1/2. Let's put the r squared next, and then we have our theta. So this is the area of that pi-shaped piece, 1/2 r squared theta. Okay. So I'm going to put a box around that. And now let's look at a general polar curve, something that's, say, going like this. This is r equals some function of theta, all right? And say we want to go from theta equaling a to, say, theta equaling b. And we want to compute this area here that's enclosed between those two dotted lines and between the curve and the origin here. Well, we can start to approximate this by cutting it up into little pi-shaped pieces. Something like this. All right. Cutting it up into pieces that look like little sections of the circle. All right. All right. Let's call a sub I one of these little pieces here. Its area. Now, the area is going to be 1/2 r squared of the angle theta. Well, our r is really f of theta. It's an angle of theta, so this is 1/2 f of theta, some theta sub I squared. And then the theta here is really the change in the theta from one to another. The angle here we're going to call delta theta. So that's the change right here, delta theta. That's our angle right there. And then basically that's the approximate area of one of them. So let's sum these up then. So the total
The
area
break will occur at a different time in the third, fourth hours.
is going to approximately equal this summation from I equals 1 to n of 1/2 times f of theta sub I squared times delta theta. And then when we take these, make more and more of these wedges, so the limit then, as n goes to infinity, we have more and more of these wedges, this will give us this, that the area is now equal to, not approximately, but equal to the derivative from a to b of 1/2 f of theta squared d theta. I replace the delta theta with the d theta, and I replace the summation with the integral sign. So let me rewrite this, because this is the formula you'll need to remember. The area under a polar curve between theta equal A and theta equal B is the integral from A to B of 1/2 f of theta squared d theta. Another way that I could write that is this. Remember, f of theta is equal to the r. So I could write this as the integral from A to B of 1/2 r squared d theta. So that's a formula that you guys need to remember then. Okay. So let's do an example here of this, a couple of examples. That might see us through the end of the class here. We'll go back to that four-leaved rows deal. R equals the cosine of 2 theta, the four-leaved rows. And let me just draw a rough graph of this. We have one petal here, one petal here, one here, and one down here. Okay. Now, what I'm asked to find is this. I'm asked to find the area enclosed by one of those loops. Find the area enclosed by one loop. All right. So the thing is, we need to find out, so let's use this loop right here. It doesn't matter, they're all going to have the same area. They're all identical that way. We need to find out what our limits of integration are. In other words, what's my angle down below and what's my angle up above? Now notice that's going to happen when this thing closes in on itself. So we're going to look at where r is equal to 0, because that's when it's going to go down to the center. So we solve r equals to 0, which means we solve cosine of 2 theta equaling 0. Okay. Well, when does the cosine equal 0? At pi over 2 and at 3 pi over 2, right? So we know the cosine equals 0 at pi over 2, for instance, and at 3 pi over 2. So therefore, let's set 2 theta, our angle of that's behind the cosine, set 2 theta equal to pi over 2, and let's see what angle we get there. Well, divide both sides by 2, and we get that one of our angles is going to be pi over 4. So this angle right here is pi over 4. Okay? All right. Now let's look at, let's see here. Okay, let's look at 3/2 pi. So we have 2 theta equals 3 pi over 2. 2 theta equals 3 pi over 2. So Okay. What's that going to give us then? When we divide by 2, we get what? We get 3 pi over 4. So that's not the one that we want. What's another way of saying 3 pi over 2, though? Because notice 3 pi over 4 is this one here. And we could use this one, that's fine. We could go from here to here, that's okay. But another way to represent 3 pi over 2 with a negative angle is what? Well, 3 pi over 2 is going like this, right? Okay, so if I want to go in if I want to represent it going negatively, it would be negative what? Negative 90 degrees, negative pi over 2. So I could also then say that negative pi over 2 is another place where cosine is equal to 0. And if I set 2 pi equal to minus pi over 2 and divide by 2, I get negative pi over 4. So this angle right here is negative pi over 4, right? Oops. Oh, you guys, I'm sorry. Ugh. Okay, so that's negative pi over 4. So basically, we can integrate this thing from negative pi over 4 to positive pi over 4. That's our limit of integration. Does everybody see that we have to figure out what those angles are, first of all, in order to do this definite integral? So we have negative pi over 4 to positive pi over 4. Now, what's our formula? It's 1/2 f of theta squared d theta. Well, what's our formula? Our r. Our r here is cosine of 2 theta. So this is from minus pi over 4 to pi over 4 of 1/2 cosine squared of 2 theta d theta. All right, 1/2 r squared. Now, let's look at this graph here for a second, just again. Okay, I'm integrating here from minus pi over 4 to pi over 4. Could I possibly just start at 0 to pi over 4? And then multiply it by 2? Kat, Jenna, what's your question?
Why is it cosine squared theta, isn't it? Because r is equal to
R is equal to cosine of 2 theta?
how is that cosine squared?
Because the formula is 1/2 r squared d theta, right here. If r is equal to the cosine of 2 theta, then 1/2 r squared is 1/2 cosine squared of 2 theta. I'm just plugging in the formula. Okay? All right. Okay. All right. I'm back to this thing about, okay, do I have to go from minus pi over 4 to 4, or can I make life a little bit easier for myself and just go from 0 to pi over 4? There's the same amount of area here as there is here.
Did you get 0 if you did that then?
No. No. Okay, I'm just going to go with think about it. And I'm just going to go with the minus pi over 4 to plus pi over 4. But you could have the area and then multiply it by 2, and you'll get the same answer. All right. So let's try to figure this out. So we've got to figure out the antiderivative of cosine squared of 2 theta. So what kind of formula are we going to use for that? Exactly. We're going to go back to the formulas that we're all going to be familiar with. Is 1 cosine squared of alpha is 1/2 times 1 plus the cosine of 2 alpha. And in this case, our alpha is equal to 2 theta. So our integral then is minus pi over 4 to pi over 4 of 1/2 times, now the cosine squared of 2 alpha is going to be 1/2 times 1 plus the cosine of how many alpha? It's got to be double. Remember, this goes from alpha to 2, to double it. If I'm starting out with 2 theta, then what am I going to have here? Right. Okay. So this is what we have. Does everybody see that? I mean, that's the thing with having to know those formulas in order to be able to get these antiderivatives. Everybody okay with going from here to here using that formula? All right. Let's distribute this out. Minus pi over 4 to pi over 4. I'm just going to distribute out stuff here. So 1/2 times 1/2 times 1 is 1/4 plus 1/2 times 1/2 times the cosine is another 1/4 times the cosine of 4 theta d theta. All right. So now I've got 2 terms here I can get the antiderivatives of. The 1/4 is going to be 1/4 theta. What's going to be my antiderivative of 1/4 times the cosine of 4 theta? Don't we just divide by whatever coefficient is on the inside? So I have a 4 theta on the inside, so I'm going to divide by 4 out front.
1/16 sine 4 theta?
Yes, 1/16 sine of 4 theta. And you can check it by doing the chain rule, and you'll find out that that derivative of that gives you 1/4 cosine of 4 theta. So you just take the number here, you're going to divide it, so that's 1/4 times 1/4, and then the antiderivative of the cosine is the sine. And then we have ready to do our limits of integration, pi over 4 to minus pi over 4 to pi over 4. So let's fill this in then. So we have 1/4 times pi over 4 plus 1/16 times the sine. Now this is 4 theta, so 4 pi over 4 is going to be pi. And then we subtract, and we're going to fill in our negative pi over 4. So this is going to be 1/4 times negative pi over 4. So 1/4 times minus pi over 4 plus 1/16 times the sine of 4 times negative pi over 4. So that's the sine of negative pi. So a lot of this stuff is going to go away because the sign at pi and at negative pi is 0. So what I end up with here is pi over 16. That is 0. That last one is 0. And be careful, I have a double negative here, so I have another plus pi over 16. And then joining them together gives me pi over 8 as my area, right? Okay. When you're doing this kind of a problem, it can really help just to do a rough drawing of it, of the curve, because you can actually simplify the problem for yourself. If we did a rough drawing of this curve is like this. We're wanting to get the area of one of the petals. If you can see here that this thing is symmetric around both the horizontal axis and the vertical axis. These axes cut these leaves in half. I could have just as well have gone from 0 to pi over 4. But if I did that, I would only get half of my area. So I have to compensate that by multiplying in front by a 2, all right? So you can make life easier for yourself a lot of times if you recognize the symmetry that you have here, so that it's easier to use 0 than it is to use pi over 4, okay, as a limit of integration. So that's all I'm saying. You can certainly get the correct answer the other way. It's just a little bit easier if you recognize the symmetry that you have here. Okay. Well, we'll see what happens here. Here's another kind of problem that you might encounter. We're finding area again. But now we're finding area between one curve and another curve. So let me show what I'm talking about. Find the area of the region that lies inside r equals 3 sine of theta, and outside r equals 1 plus the sine of theta. This is our heart graph, our cardioid. All right? Let's just try to do a simple graph here. The cardioid is going to look like this, or something like that. This top one is going to have a single leaf to it. It's sine of 1 times theta. 1's an odd number. This top one is going to look like this. All right? What we're talking about then is trying to find the area that's above the cardioid and below r equals 3 sine of theta. So it can be very helpful just to draw a very rough graph of what you're trying to find. Now the thing is, we have to find the limits of integration. That means we have to find out where to start here and where to start here. Okay. What happens here at these 2 points? The curves equal each other. That's where the curves join each other. So, set the 2 curves equal to each other. Equal to each other. And solve for theta. All right, so let's do that. So our one curve is 3 times the sine of theta, and our other one is 1 plus the sine of theta. So let's get all the sines of theta on one side by subtracting. So I have 2 times the sine of theta is equal to 1. And now let's divide by 2. So we get the sine of theta has to equal 1/2. So what angle can we think of right away whose sine is equal to 1 over 2? Yeah, pi over 6, sine of pi over 6. So this angle right here is going to be pi over 6. Any guess to have, so remember, A, S, T, C. Want to hazard to guess what that angle on the left is going to be?
5 pi.
Right, 5 pi over 6. It's just going to be 1/6 off from the axis there. So pi minus pi over 6 is going to be 5 pi over 6. It also has a sine equal to 1/2. So trigonometry is alive and well. All right, so therefore this is what we have to set up, and we may not get any further than this today then. Okay, so we have our limits of integration then. The one is pi over 6. The top one is 5 pi over 6. Now, basically to get this, we have to take the area of the bigger one and subtract from it the area that is in the smaller space. This area here, we want the area between those two curves. So basically that area is going to be the area that we get from the bigger one minus the area we get from the smaller one. Does that make sense? The difference of the two areas. So it's going to be equal to the area of the bigger minus the area of the smaller. So let's set this up. Okay, if we know it's 1/2 r squared. So for the bigger one, it's 1/2. Now what is our bigger one? Our bigger one is 3 sine of theta. So it's 1/2 times 3 sine of theta squared. Then it's minus, it's still in the integral, 1/2 times the smaller one. The smaller one is our cardioid, 1 plus the sine of theta. So that has to be squared. 1 plus the sine of theta in parentheses squared. And then we have d theta after that. So this is the integral we have to set up. 1/2 r squared for the bigger one minus 1/2 r squared of the smaller one. All right? Are we okay with that idea? Let's see what we get here. You know, I could just keep the 1/2 there. But 3 sine of theta squared is going to give us what? It's going to give us, 9 sine squared of theta. I'll put the 1/2 again, minus 1/2. And then to square this out, I need to FOIL it. 1 plus sine of theta times 1 plus sine of theta. FOIL it out. So let me put some more parentheses here. So that gives me 1 plus 2 sine of theta plus sine squared of theta, d theta. All right, so I end up with a bunch of terms. And it's not going to be that bad. All right. Let's see what we can do here with this in the few minutes we have left. Notice I've got a sine squared of theta, and I also have another sine squared of theta over there. Could I combine those into a single term? This is all in the integral. What would that be? That'd be, I have 9/2 here minus 1/2 there. So what's 9/2 minus 1/2? I have 4 of those, right. I have 4 of these sine squares of theta. All right. Now what else do I still have here? Because I have to make sure everything's accounted for. Then I have minus 1/2 times 1. So that's minus 1/2. And then the other thing I still have to have is I have minus 1/2 times 2 sine of theta. All right. So that's going to be what? Minus 1/2 times 2 is minus sine of theta, right? Okay. So I basically end up with this. Okay. From pi over 6 to 5 pi over 6. Now, what can I replace that by? That's one of those squares. What's the sine squared of theta? No, that's replacing a square with a square. We want to get rid of the squares.
So 1/2, 1 minus 6.
Right. The way I told you guys that I remember that is sine is sin, is bad, so we're going to have a negative there. Okay, that's how I remember this stuff. So this is 1/2, 1 minus the cosine of 2 theta. All right? And then this is still my minus 1/2 and my minus sine of theta, like that. All right. So actually, we're almost finished with this thing, so we might as well pretty much finish it. Okay, what would I do next then with this thing? Let's run a test. What would I do next?
Distribute everything.
Yeah, get rid of those parentheses. Let's distribute. We have 4 times 1/2, that's a 2. So that's 2 minus 2, 4 over 2, cosine of 2 theta, minus 1/2 minus sine of theta, all right? And then 2 minus 1/2 is 3/2, so let's do that. So 3/2 minus 2 cosine of 2 theta minus sine of theta, all right? And then we've reached the end of the road for simplifying, all right? So we've had to use this formula, sine squared of theta equals, we've had to combine terms. So this is what we have now, from pi over 6 to 5 pi over 6. Okay, d theta. So now we can get the antiderivative of each of those 3 terms and go from there. So 3 over 2 is going to give us 3 over 2 times pi for the antiderivative. Times theta, thank you. What's minus 2 cosine of 2 theta? What's its antiderivative going to be? Yeah, be careful with that, yeah. Okay, derivative of the sine is the cosine, so Art, would we be changing signs? Yeah, it'd be negative sine 2 theta. Look at this. We have a minus 2, but we have a 2 here, so we have to divide by that. And the antiderivative of the cosine is the sine. So basically, we have what Jordan said, minus sine of theta for the antiderivative. And then we have another And then the antiderivative of the minus sine is the cosine, plus the cosine of theta.
Isn't it sine 2 theta?
Oh, yes, thank you so much. It absolutely is, yes. All right. Thanks, Jenna. So now we have it, and now we plug in the pi over 6 and this should be 5 pi over 6. Okay. And I don't think I want to go through all of that. I'll tell you what we end up getting, though, is we end up getting a very nice final number of pi. All right? When we plug those things in. The last thing I want to say, I promise today, the last thing I want to say is this. We could have made this problem at the end easier, a little bit easier, look at our original drawing here, where we went from pi over 6 to 5 pi over 6. This thing is completely symmetric about the center point right here. In other words, there's as much area here as there is here. I could have just gone from pi over 6 to pi over 2, but if I did that, I would have to multiply in front by a 2, all right? So I could have changed my limits of integration, because pi over 2 is always easier than 5 pi over 6.